Just think of life without paper, no notebooks, books, newspapers, currency notes, checks, certificates, etc. The magazines carrying beautiful photographs and interesting stories would disappear from our life. It would have been a really different world, right? Do you know, from the sugar we eat to the cotton we use for fabrics and the paper for writing are all made up of organic compounds containing hydroxyl groups, or we can say alcohol. Alcohols and phenols are formed when a hydrogen atom in an aliphatic and aromatic hydrocarbon is replaced by hydroxyl group. These classes of compounds find wide applications in industry as well as in day-to-day life. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryloxy groups yields another class of compounds known as ethers. You may also visualize ethers as compounds formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this video, we will discuss the classification of three classes of compounds, namely alcohols, phenols, and ethers. Let's start with the classification of alcohols and phenols. Depending upon the number of hydroxyl groups, alcohols and phenols can be classified as mono, di, tri, or polyhydric compounds. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. In this class of alcohols, the OH group is attached to a sp3 hybridized carbon atom of an alkyl group and is further classified as primary, secondary, and tertiary alcohols. If the hydroxyl group is attached to an sp3 hybridized carbon next to the carbon-carbon double bond, then that is an allylic alcohol, as you can see. Whereas, when the hydroxyl group is attached to an sp3 hybridized carbon next to an aromatic ring, then it is called benzylic alcohol. Next, if alcohol contains hydroxyl group bonded to a sp2 hybridized carbon atom or carbon-carbon double bond, that is to a vinylic carbon or to an aryl carbon, these alcohols are also known as vinylic alcohols or phenols. In case of ether, they are classified as simple or symmetrical ethers if the alkyl or aryl groups attached to the oxygen atoms are the same, and it is mixed or unsymmetrical if the two groups are different. Diethyl ether and dimethyl ether are symmetrical ether, whereas the other two are unsymmetrical ethers. Let's now discuss the nomenclature of alcohol. The name of an alcohol is derived from the name of an alkane by substituting E of an alkane with the suffix -ol. Thus, CH3OH is named as methanol and C2H5OH is named as ethanol. Whereas, the common name of an alcohol is derived from the common name of the alkyl group and adding the word alcohol to it. For example, CH3OH is methyl alcohol and C2H5OH is ethyl alcohol. In the case of alcohol having more carbon atoms, the longest carbon chain, that is the parent chain, is numbered starting at the end nearest to the hydroxyl group, that means here. The positions of the OH group and other substituents are indicated by using the numbers of carbon atoms to which these are attached. Therefore, the IUPAC name of isobutyl alcohol is 2-methyl-propan-1-ol. For naming polyhydric alcohols, the E of the alkane is retained and the ending -ol is added. The number of OH groups is indicated by adding the multiplicative prefix di, tri, etc. before ol. The positions of OH groups are indicated by appropriate locants. For example, glycerol is termed as propane 1,2,3-triol. In the case of cyclic alcohol, they are named using the prefix cyclo and considering the OH group attached to C1, as you can see here. In the case of aromatic compounds, the simplest hydroxy derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. As the structure of phenol involves a benzene ring, in its substituted compounds the terms ortho, that means 1,2-disubstituted, meta, 1,3-disubstituted, and para, 1,4-disubstituted are often used in the common names. On the other hand, in ethers, the common names are derived from the names of alkyl or aryl groups written as separate words in alphabetical order and adding the word ether at the end. For example, CH3O C2H5 is ethyl methyl ether. If both the alkyl groups are the same, the prefix di is added before the alkyl group. For example, C2H5O, C2H5 is diethyl ether. Now let's have a look at the structures of alcohol, phenol and ether. In case of an alcohol, for example methanol, the oxygen of the OH group is attached to a carbon by a sigma bond formed by the overlap of a sp3 hybridized orbital of carbon with a sp3 hybridized orbital of oxygen, and the bond angle in alcohols is slightly less than the tetrahedral angle, that is 109.5 degree, due to the repulsion between the two unshared electron pairs of oxygen. In the case of phenols, the OH group is attached to an sp2 hybridized carbon of an aromatic ring, and the carbon-oxygen bond length is 136 picometer, which is slightly less than that of the methanol. This is due to the partial double bond character on account of the conjugation of unshared electron pair of oxygen with the aromatic ring, and also due to the sp2 hybridized state of carbon to which oxygen is attached. In ethers, the two bond pairs and two lone pairs of electrons on oxygen are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the two bulky alkyl groups. Here the carbon-oxygen bond length is 141 picometer. Now that we have come to the end of this video, can you classify the following compounds as primary, secondary and tertiary alcohols? Well, to answer this, recall the classification of alcohols. Now let's summarize what we have learned.
Manorama Horizon. Learning made simple.